Hello everyone, myself Rajale I am from RBNB College, Sri Rampur. My subject is mathematics. In today's lecture, we go with the concept of the chapter matrices. In that, our first concept is we have to define the matrix first. That is, we have to see definition of matrix. To define the matrix, we consider the rectangular arrangement, okay, and in that we consider mn elements, total mn elements arranged in m rows and m columns. Try to remember again. Here in matrix, we consider the rectangular arrangements of mn elements arranged in m rows and n columns. Okay, so we see some examples to define the matrix. Let us consider here A is the first one, and this matrix is having in first row 2, 1, and in second row 4, 5. So here in this matrix we consider 2 rows and 2 columns. So here order for given matrix is here 2 by 2. So we arrange the elements of the matrix in the in this bracket or in this closed bracket. Okay, then we consider another one. Here B is the another matrix and is having here in first row 1, 2, 1, then here 3, -1, 5. In this matrix, there are 2 rows. This is our row first and this is our row second. Then in that we consider 3 columns. Here this first is C1, this second is C2, and this third is C3. So in this matrix we arrange the elements in rows and columns. Let us see one more example to define the matrix. Okay, here C is the another matrix and is having here 2, 1 in first row, then 2, -1 in second row, and in third row we consider 0, 5. Again, in this matrix there are 3 rows. Okay, so here this is our first row, then here this is our second row, then here this is our third row. Then in that we consider total 2 columns. Okay, so here this is our column first, then this is our column second. So order for this matrix is here 3 by 2, that is 3 rows and 2 columns. In that also we consider total 2 rows and 3 columns. So order for given matrix is here 2 by 3. Here this 2 is for rows and this 3 is for columns. So we define the order of matrix like this. If in our given matrix we have total m rows and n columns, then order for this matrix is m by n. Remember again, here m is for rows and n is for columns. Okay, so in this chapter we are going to see important concepts related with the this matrix. Okay, so we go with our first one. Here first is for elementary transformations. Elementary transformations. Okay, very interesting part it is. Here there are total 6 operations, that is there are total 6 transformation. In that 3 is for rows and 3 is for columns. Let's go with our first one. Here in first we consider interchanging any 2 rows any two rows or any two columns Okay, to define this concept, we consider two rows. Let here Ri is the first one, then Rj is the second one. We consider these two rows. Okay, then here we denote this concept, that is we have to interchange the rows, that is here Ri interchange with Rj. We denote this by using here Ri interchange, that is double implies Rj by using this notation, or we denote this by using simply Rij. So remember this point. Here we interchange our ith row with the jth row. This is for rows. Now we consider columns. Let here Ci and Cj be the two columns. If we have to interchange ith column with the jth column, then we denote this by using here Ci double implies Cj by using this notation, or we denote this by using here Cij. So remember this point also. This point is very important. Okay, let us see example depending on this. Let A is the given matrix, and this matrix is having 3, 1, 0, 2. We know order for this matrix is 2 by 2, since here 2 rows and 2 columns are given. Okay, let us consider, or we interchange our first row with the second row. Symbolically we denote like this. R1 double implies R2. That is, we have to interchange our first row with the second row. So here new equivalent matrix is here inside the close bracket. Here we interchange our second row. This second row is having elements 0, 2. We consider these elements in first row. So 0, 2 in first row. Then here in row first we have elements 3, 1. We take these two elements in second row. So here 3, 1. So this is our new equivalent matrix. Let us see one example for column. Here again A is the given matrix. If we have to interchange our first column with second column, then we denote this by using C1 double implies C2, or we consider here C1, 2. Okay, so here new equivalent matrix A is having, now consider column first. In the column first we have elements 3, 0, and in column second we have 1, 2. So we consider 1, 2. This 1, 2, that is elements from column second for column first. So here in first column 1, 2. Then we consider 3, 0 in the second column. So here we interchange our first column with second column. So in this part we consider some examples related with how to interchange our rows or how to interchange our columns. Let us see another one, another transformation, multiplication of the elements of any row or column by non-zero scalar. Let us consider the non-zero scalar. let K is the non-zero scalar. K is non-zero scalar. Let us consider our one row. Let Ri be the given row. Ri be the ith row. Ith row. Then here multiplication of the matrix and the non-zero scalar is denoted by using here K R I. Remember this. This is the notation for the multiplication. That is scalar multiplication. Here we multiply each element of the ith row by K. That is by non-zero scalar K. Or we denote this by using here Ri implies here KRR. KRI. Okay. Here we perform the operation on ith row. And operation is here KRI, that is we multiply each element of the ith row by using the constant or non-zero scalar K. Now for the column, we consider for the column, again we consider the non-zero scalar. Let K is non-zero scalar. K is non-zero scalar. Again we consider one column. Let Ci be the ith column. Then here multiplication is denoted by using KCI. That is, we multiply each element of the ith column by non-zero scalar K. Or we denote this by using here Ci implies KCI. That is, we perform the operation. We perform the transformation on the ith column. And the transformation is here KCI, that is we multiply each element of the ith column by non-zero scalar K. So remember this point also, remember this transformation. We see first for the row, then here we see for the column, how to denote this multiplication. Let us see example. Okay, example, let A is the given matrix and is having 1, 2, 3, 4. Okay, this matrix is having order 2 by 2, that is having 2 rows and 2 columns. Let us consider the transformation. Let, or here I write directly, row first implies 5R1, that is 5R row first, 5 row first. Okay, now here we perform the operation on this row first, and the operation is here 5 into R1, that is we multiply each element of the row first by the 5. So here in this example, A is equivalent to here inside the matrix. Now we multiply each element of the row first by 5. Here everyone knows 1 into 5 is 5. Next here 2 into 5 is 10. So we perform the operation on only row first. Then we keep the second row as it is, that is 3, 4. So this is our new matrix. This is our new matrix. Now we consider for the column. Here again we consider the same matrix. Here A is the matrix having the order 2, that is 2 rows and 2 columns. Here we consider the transformation 5, or we consider here 7C2. 7C2. Or we denote this by using C2 implies here 7C2. That is, we have to perform operation on column second, and operation is here 7C2. That is, we multiply each element of the column second by the scalar 7. Okay, so here new equivalent matrix is here inside the matrix. Here we keep our first column as it is. In the first column we have 1 3, so we keep as it is. Then we perform the transformation on only column second. We multiply each element of the column second by 7. Here 2 is given, so here 2 into 7 is 14. Then here 4 into 7, we know 4 into 7 is 28, and this is our new matrix. This is our new matrix. So for this transformation we consider the scalar and we consider some rows, or we consider the column. How to operate this transformation? For this we consider 2 examples. Let's go with our third one. Adding the scalar multiples. Adding the scalar multiples of the elements of any row or column to corresponding elements of any other row or column. Now this part is very important. We have to multiply here one row or column by the scalar, and we this add with any other row or any other column. Okay, again to define, or we denote here. Firstly, here the scalar multiples of the elements of any row. Let us consider here k is non-zero scalar. Then we consider the ith row. Okay, then we consider our second row rj. If we multiply this ith row by k, we get here k ri, and we have to add this with here rj, that is here rj plus kri. We denote this concept by using rj plus kri. This is for row. Similarly for column, here consider the scalar. Let k is the given scalar. Then we consider the 2 columns. Here ci and cj be the 2 columns. Let's multiply first column with k, so we get here kci, and we have to add this kci with here cj, so here cj plus kci. We denote like this. In this point, remember one thing, here firstly given rj, here firstly given cj, we perform the transformation on. Here in first, we perform the transformation on only jth row. That is, we have to change only jth row, not ith row. Here again, we have to perform transformation on jth column and not on ith column. Remember, so here we have to change only jth column. Let us see example for this. Example, first one is the matrix and is having here 2, 4, 1, 3. We know this matrix is having order 2 by 2, that is having 2 rows and 2 columns, that is having order 2. Okay, let us consider the transformation. Firstly go with the rows. Here R1 plus 3R2. That is, we have to perform operation on this first row and not on this row second. We have to change this row first only. So here new equivalent matrix is here inside the matrix. Okay, here we have to add this first element of first row with the elements of the second row. Here check again, check this. Here in the row first we have element 2. Okay, then plus 3 times elements of the row second. First element of the row second and is 1, and we get here 2 plus 3, and we know 2 plus 3 is 5, so here we have 5. Next, again here we consider elements. Second element of the row first, here given 4, so plus 3 into second element of the row second, here given is 3, so this is equal to 4 plus 9 and is equal to 13, so here we have a 13. So we change only in this row first, okay, and now we keep the second row as it is, that is this 1 3 as it is. So this is our new matrix. Let us consider for the column. Here we perform the transformation on row second, and transformation is here C2 plus 2C1. That is, we have to perform transformation on column second and not on column first. That is, we have to change only this column second. Okay, so here new equivalent matrix A is having, now we keep our first column as it is, since we have to change only column second, so here 2 1 as it is. Now here we consider column second. Here first element of the column second is 4, okay, then here 4 plus 2 times, here first element of the column first is 2, so here 2, and this is equal to 4 plus 4, and we get 8, so here in second column first element is 8. Now here in the column second element is 3, so 3 plus 2 into, now here second element of the column first is 1, so 2 into 1, and this is equal to 3 plus 2 and is equal to 5. So second element of the column second is 5. So this is our new matrix. So remember this point also. This point is also very important. Okay, up to all we see how to interchange our columns or rows. Okay, then in second point we consider the scalar multiplication, that is we multiply some row or some columns by the non-zero scalar k, and in last we consider where we add our row scalar multiplication k into row first with the any other row, or we consider scalar multiplication, that is KCI with Cj. Okay, so up to all we consider total 6 elementary transformations, and here 3 is for rows and 3 is for columns. Let us see some more example to define the elementary transformations. Apply the given transformation. Apply the given transformation on each of the following. On each of the following. Here in first we consider matrix A and is having here 1 0 in first row, minus 1 3 is in second row, and transformation given is row first interchange with row second. Okay, so we have to define this matrix by using this transformation. Consider the given matrix again. Consider A matrix and is equal to here in first row 1 0 and in second row minus 1 3. We have to perform the transformation and is row first interchange with row second. Okay, so our new equivalent matrix is having, now we replace our first row with by using the second row. In second row our elements are minus 1 3, so here minus 1 3 is in first row, Then we interchange our second row by using the first row. In first row we have 1 0, so here in second row 1 0. So this is our new matrix. Let's go with another example. Here in second, given A is the matrix, in first row 5 4 and in second row 1 3. Okay, here we have to perform C1 interchange with C2. Okay, consider the given matrix again. Consider a matrix and is having 5 4 in first row, 1 3 is in second row. Here transformation given is C1 interchange with C2. That is, we have to replace our first column. C1 double implies C2. Okay, we have to replace our first column by using the second. So here in the new equivalent matrix, 4 3 in first column and 5 1 is in second column. So this is our new equivalent matrix. Let us consider another one. In third example, we consider a matrix. In first row 1 minus 1 3, 1 minus 1 3, in second row 2 1 0, and in third row 2 3 1. Transformation given is C3 plus 2C2. C3 plus 2C2. Consider the given matrix again. Let here, or we consider a matrix having again 1 minus 1 3 2 1 0 2 3 1. We have to perform the transformation C3 plus 2C2. C3 plus 2C2. That is, we have to perform transformation on this column 3, not on column second. We have to change only column third column. So here new matrix, new equivalent matrix is having, now we keep our first column as it is. Here in first 1 2 2, then we keep our second column as it is. Here minus 1 1 3. Now we change our third column by using this transformation. Now we consider each element. Here first element in column 3 is 3 plus 2 times. Here first element of column second is minus 1. So 2 into minus 1, add is equal to 3 minus 2. Everyone knows 3 minus 2 is 1. So here first element is 1. Next, we consider the second element from the column third. Here is 0 plus 2 times. Now we consider the second element of column second and is 1. We get here 0 plus 2 and we know this is 2. So here second element is 2. Next, here third element of column 3 is 1 plus 2 times. Here second, last element of column second is 3. So here 3 and this is equal to 1 plus 6 and is equal to 7. So here last element of column 3 is 7. So this is our new equivalent matrix. This is our new equivalent matrix. Okay. So up to all point, we see some important examples related with the elementary transformations. These transformations are very important to find the inverse of the matrix. Okay, so remember these points. In next lecture, we go with the concept of inverse of matrix. Thank you.